This video is finally the last step of our process of getting ready to actually make a molded aircraft. So here is the simple extruded wing pair of molds. So I've got them closed up so it just looks like a box, but certainly there's more work in there than that. If you remember from the previous video, this is the bottom mold of an odd wing that's Epler 423 in the middle and I think a 0006 at the tip. It doesn't make a whole lot of sense, but we're just here for the molds and not for the aerodynamics. We'll actually be using the top mold because it's simple. We'll start with making Gcode, and the machine code is what that is. Auto-generating the paths to machine this part out, because this is really indicative of probably definitely more than half, but most simple molds are just a simple cavity. I mean, you don't want to have any over vertical elements. Undercuts is what they're really called. The other mold, if you look at it, has this odd island in the middle. You remember how we had the Epler is so under-cambered that it actually produces some positive material. There's nothing inherently more difficult about having a CNC machine cut this. It's just not the simplest, easiest place to start. So as the first example, let's start easy and then we'll add complication later. But really the complication will come from, I think it's not that part, maybe the next one. Yes, we'll do a more complicated mold being the one without a planar parting surface, and then we'll compare how long these two will take to cut out from one another. But starting simple, if you had this large wing mold and you wanted to cut it, the first thing to do is establish a coordinate system for the cut. And this coordinate system should match the CNC machine you're going to use. There are 4 things you have to define. Really, it kind of comes down to 3 because one of them's implied by the others. The first is where you want the origin of your component to be. So which corner do you want to essentially zero your CNC machine out on? In this case, if I was going to cut it out on a CNC machine where I was facing the material, kind of as shown in the window right here, I usually try to center it on the front left. For whatever reason, that's just my habit. There's nothing more correct about that than any other path. But it's just accessible towards the front of the part and the left side. I don't know. That's where I put it. Top of the material, so that way whenever you touch off, you can touch off on the material block before you cut it. You can set it towards the top. It very easily, if you want to, with molds, basically everything is referenced to this top surface you're going to be cutting. So if you wanted to push that 0 down into the material, maybe 1/4 of an inch, 1/8 of an inch, to take off any sort of surface imperfections. Maybe the material, the mold blank got dinged in shipping. You want to make sure you have a nice flat parting surface. You could recess that point at the machine side a little distance, because some of the alternatives is like, well, okay, you could put this point at the bottom, so it's actually at the work table of the machine, and then your code would exist, whatever that is, 2 inches, 3 inches above that origin point, and you'd be cutting everything there. But then if you want to adjust really the thickness of the mold or compensate for any sort of surface defect, you have to go back and regenerate your code and some other things. I don't know. There are a few reasons that I like doing it on the top surface, and none of them are all terribly compelling or important. So we'll move on. The X and Y axis, this is something to check with your machine, because sometimes the entire direction the gantry moves will be the X axis, sometimes the traverse direction will be the Y, and then sometimes the machines have it switched. So just check your machine setup. Look at a code that you know how it ran on the machine or how someone else has run it before on the machine. In this case, I'm going to set, I believe on our machine, the X axis is the long axis, the Y axis is the shorter axis, and Z would be positive up. And that's what I meant by you usually have to define 3 of the 4 elements, because, well, that 4th vector of the triad becomes set. If you did need to change that Z direction, you could change which direction Y is positive in. The vectors are pointing in the positive direction, and that combination creates the result of Z being positive up. So that coordinate system is what I want, and I'll say OK. So note that you've done this before even starting any sort of Gcode or code generation. The program we'll be using today, in fact, I'll pull it up real quick on a website. It's called HSM Works. And for now, this is 2019 when the video is being recorded. I really like this solution, and it's actually owned by Autodesk. Now, Autodesk, the company, liked the HSM solution so much, they purchased the company, made it a part of Autodesk products, but thankfully they still offer the addition to SolidWorks. With academic educational license possibility, you can make an account, sign in, get a free download. It's really, really, really a good piece of software. There are a multitude of CAM, computer-aided manufacturing softwares out there, and they make a big difference in your happiness while generating this code. Most all of them are successful. They couldn't sell software unless it was able to generate code, but certainly the quality of the auto-generated code, the speed at which it removes material, and overall just the usability of the software is the biggest difference I see between things. So I would highly recommend HSM Works right now, at least, over some of the more default SolidWorks CAM options. And maybe you'll agree with me or disagree by the time we're done with this. So starting with a simple mold, we're going to go through some of the typical operations you might do. Notice that I have a CAM tab now because I've installed HSM Works. I've already got all the licensing stuff handled, all the installations done. That should pop up once you have it there, and it's kind of nice because now you see we can actually do all these different kinds of toolpath generations. It can do CNC lathes, CNC mills, all the way from what's called 2.5 dimensions of CNC milling up to 5-axis. I don't know if the educational version does 5-axis or not. I've never had a 5-axis machine to play with. So this is where we're at. We have the coordinate system. Let's go ahead and go over to the milling tab, which right now we see we just have nothing. We've made no parts. We've made nothing. So start with the job box. That's where we start things, and it automatically sizes our material stock. It knows how big your part is, and thankfully it can contain all of that solid within one big prismatic chunk of material. So thankfully that's no big deal. It's already also detected we created a coordinate system, but I like to check that. So you can either use the default, the origin and orientation of the whole part, but notice those arrows don't match what we want. The origin and orientation of the part matches the triad of SolidWorks down here, X, Y, Z. Notice the colors and directions match. That's not what we're going for. Use coordinate system. Just make sure the coordinate system you want is selected, because that's going to be the coordinate system the entire job is set up in. So okay, and I think that might also be where you switch between, yes, milling and turning. So if you have a CNC mill, do that. If you have a CNC lathe, which this part is not suited for, you would switch that understanding there. That's where the big major toggle is. So to go over overview here, drilling is really just for operations where you'd be using a drill bit, whether it has coolant feed through it or whatever, and there are different drilling strategies. I guess there's not many different drilling options here. But if you do have a part where you're just maybe making like a pegboard, it would do like multiple taps. You can do plunge speed. There's lots of different preferred methods, lots of different material reasons you might choose one method of CNC drilling over another. But like I said, we don't really mess with that a whole lot on our CNC milling. 2D milling is great for cutting out bulkheads, cutting out shapes out of maybe fiber reinforced plywoods. If you make some flat stock and you want to cut your airplane ribs or, like I said, bulkheads, longerons, motor mounts, etc. out of it, then really in 2D milling you'd go down here. I think 2D contour is the most useful tool process. But we don't have 2D molds today, so we're going to be going straight to 3D milling. Let's say straight to 3D milling. We actually will start in a 2D process called face. Because the first thing we want to do is make sure that our flat planar parting surface on this mold is faced off correctly. To do this, we need to define a tool that we're going to use in the CNC machine. The code needs to know what tool it's going to be cutting with before it can properly generate a path. So you have a bunch of inbuilt tools. Like, let's see here, we could go to inch-sized tools that are good for, well, we're cutting, I guess, foam, so I guess even aluminum tools will be fine. So they have a ton of inbuilt pre-done tools. Now, you might say, okay, well, what if the tool I want isn't here? Well, don't use a sample library. Let's create a new mill tool. Well, that's okay. That's fine. My libraries. Yeah, let's make it there. Oh. Okay. We'll just create the new mill tool inside of the part. It just wanted to have a place to save it. So we're actually going to be saving this tool definition inside of the part. That means we have to redefine it every single time, but honestly it's probably a pretty good practice, so you make sure you're using the right tool for the cut you want. The tool number is handy if you're working with a machine that has ATC. So it'd be able to select tool number 1 or tool number 10 or tool number whatever. That's where it tells the machine what slot the tool is going to be in. Coolant, you could say disable or flood or mist. You can pick any coolant process you want because our machine doesn't have automatic coolant. Plus, if you're cutting foam or MDF for a mold, then yeah, coolant's not required at all anyway. So you can say disable, but it doesn't matter if you leave that on. The most important page here, and that looks like a crazy picture of a cutter, and that is a pretty wild face cutting mill, is here. On the cutter page, let's go to a flat mill. We're going to go pretty standard. This just describes any kind of cylindrical mill with a flat face. And if I think, looking at the tool that I have here, it's 1 inch wide, and the shoulder goes up not very far on mine, maybe 2 inches, and the flutes really are only about 0.5 inches. But this is fine for facing. Like, we're just going to be flattening off the top, so really it's this wide bottom face that's going to do most of the cutting, maybe a 1/16 of an inch of depth. We're not going deep with this tool, we're just flattening the top surface. So we'll say, okay, 1 inch shaft diameter, actually I think it's 0.5 technically, so the tool looks more like that. These are approximate. What you would really be doing at this stage is hopefully having the tool you're going to cut with in your hand with a set of calipers, measuring diameter, or taking measurements on the tools. If you're holding any of these tools ever, keep in mind those edges, by definition, are extremely sharp. Be careful. Okay, so if you wanted to define a tool holder, you can actually have a three-dimensional tool holding shape, so you can prevent your cutting head from running into your mold. HSM Works will actually check to see if the CNC machine itself, positioned above the cutting bit, will actually strike the side of a mold or it'll interfere at any point. So if you define a 3D model of your machine, you can actually have it check here. Same with the holder and geometry and everything else. Feeds and speeds. If you've ever been around CNC machinists or machinists of any kind, yeah, this is a big deal. So we have 2 flutes. If you know the speed of your spindle, you can set it here. If you're working with a machine that has what you might call a CNC controlled RPM setting, where the motion controller can set the RPM of the spindle, then this speed is very important. Our machine, you turn the spindle on or you turn it off, and the speed adjustment is on the side. It's actually just a router, a handheld router head, and it's a simple part. It's a cheap part, so that way, if while learning, if you make a mistake, it's not going to cost us a ton of money to fix. Cutting feed rate, extremely, extremely important number to set. Our machine really should never go above 50 inches per minute. That's probably plenty fast enough. For various reasons we can discuss, mainly being the inertia of the machine, the strength of the stepper motors involved, the horsepower of the spindle, on and on and on, 40 to 50 inches per minute is fine. Some high-end machines in industry can be over 1,000 inches per minute, and sometimes over 100 through hard metals like aluminum. 1,000 would be probably in some very light material like foam. So anyway, let's look at, cutting feed rate 40, lead ends. This is when you're entering the part. This is when you're exiting the part. Ramp feed rate is when you're actually descending down into material. So being a bit slower there is a bit better. And all of these numbers kind of come out in combination with RPM to generate a feed per tooth. And basically this is the depth of cut each individual edge will be taking as it's progressing through material at 40 inches per minute and spinning at 5,000 RPM. Now these are actually more like what might you call it? Convex slices, the little crescent moon shaped slices. So the depth isn't exactly constant all the way through, but the chip load, the feed per tooth, is really kind of what you're looking at. So okay, 40 inches per minute sounds pretty good. We'll say okay. There's our tool selected. We'll say okay. It duplicates a lot of these numbers here for you, so you can check as you're going through. Because I like this process, you can basically go 1, 2, 3, 4, 5 through the tabs up top. That sets up the cutting process you want. So the second tab is called geometry. We want to select some stock contours. Basically, I want to face off, the flat face of that part. That should be okay. This page shows the different retraction planes. So clearance height is how high above the part you're going to be going if the machine wants to go from one place to another. Retract, feed height, top of the part, bottom of the part. And yeah, this is very simple because there's really no depth to this cut. It's all flat. So you can see there's hardly any interesting dimensions. So retract height would be 0.2 inches up. 0.4 inches above that would be how high the clearance height should be if it really wants to be clear of the part. Like so, for example, if we raise this to 1 inch, it goes much higher. CNC machines, motion-wise, should be accurate easily to 1/100th of an inch, around about that height, around about that dimension. Many higher quality ones are much better, down to 1,000th of an inch. So what I'm saying is 0.4 inches or 0.2 inches should definitely clear your foam piece, your work piece. So usually these don't have to be touched or messed with as long as the code has automatically identified the top and the bottom of your part just fine. Passes is where you really want to start paying attention to the individual settings of your cut definition. The arrows should indicate the principal direction of traverse in this facing operation. Tolerance is how close you want to get to the surface. We should be able to get almost exact tolerance because it's a flat surface, no big deal. This should be step over. Yeah, so we have a 1 inch wide tool that's going to step over by 0.95 inches. So this means that the tool in this case has very simply a 95% engagement with new material. This is larger than typical, but it's okay for a face milling operation where you just have a very light cutting load. If you're going down into a mold where you're moving a bunch of material at once, you would want this engagement probably to be at 50% of the tool width or less. If you really wanting a nice surface, then you start worrying about some scallop heights, which we'll discuss later in other operations. Okay, so let's see. We don't need multiple depths. Both ways cutting. Yes, please. That should be fine. Lastly, basically mess with the lead-ins, lead-outs. So for the lead-in entry, yeah, I don't see any reason to change anything listed here. Basically, lead-ins are how it descends down into the material. And the thing I really like about HSM Works as well is if you ever have a question about what's going on, just hover over an element, and it usually comes up with a picture and a description, and it's very easy to learn what each individual little input box means. So we'll accept this operation. It automatically generates the path, and that's what it's going to show for us as being the facing operation of that entire flat molded surface. Now this again comes down to the fact that we have a flat planar parting line. This is why it's such a big deal for machining. It's very, very simple. It's very fast. We're using a flat tool to make a flat surface, so the offset can be huge. And yeah, we're good. But certainly this will not alone make the part we want. Everything on the inside here is, untouched. So let's now go to a 3D milling operation, and I want to do this in 2 steps. The first step, I will use the same 1 inch tool that's already loaded in the machine, so that way we don't have to stop and change tools and load something else and proceed on. And we'll do a roughing pass to remove a bunch of the material that exists inside of this cavity. So let's do, so there are many options here, and many of them don't work well. We principally use spiral, morph spiral, and pocket clearing or contour. So let's see if contour will generate the path we want. So there's our tool definition. It's actually still the same tool as before. Geometry, machining boundary, silhouette, selection. Let's machine that one and that one. Notice it's actually, this red line defines a silhouette that the tool is going to stay inside of. Saying the tool can actually be outside the boundary, just touching it externally as depicted here in the third picture over. You have different selections. Let's keep the tool center at least. Since it's roughing, let's keep it inside. There are retractions and heights. Notice now it actually detects the actual bottom of the model as the real bottom, so that's no big deal. Worked out. And here we start to get into some more interesting settings for contour operations. We have a depth. Is this material to leave, or is that maximum step down? We want definitely a larger step down than 0.04 inches. We have a beefy, strong 1 inch wide milling bit in this scenario, so I'll say we're going to step down at least 0.5 inches from one level to another. Since it's a roughing pass, I don't really want to bother with shallow areas. As you see in that picture, it basically adds additional passes, almost like a 3D printer would, in regions of very shallow slope. Okay, since it is a roughing pass, stock to leave is a nice option. This means that it will stay away from the actual material surface that you're going to do in the final finishing pass. In this case, I set it to 0.1 inches. That means that it's going to just leave some material for that final pass to take off, and that prevents any sort of edges or cuts from your roughing pass showing up in your final. So, okay, I think that's pretty good. The lead-ins... ramping is how it actually goes into the part. Plunge is just doing it, what I might call simply or stupidly. It's where the tool just goes straight down. It plunges straight into the material. That's usually hard on the tools, hard on the cutters. It can lead to some broken stuff. So helix lead in is probably pretty good. is there an angle? So yeah, 2-degree lead in. That's pretty shallow. So let's do a 10-degree. That keeps you from having this, like 14 revolution, 50 revolution helix lead in. So say OK to the contour job. It automatically generates the path, and we'll see if what I've selected makes any sense. No, not the solution I was looking for. I mean, it is staying away from the outer surface, but I want it to... Contour might be superior as a finishing path, but not for roughing things out. Let's show you why. So if I select that contour path and I say stock simulation, this actually shows the material before it's cut, and you can you slow the speed down a bit and you press play. It will alert you with red indication here and warnings here. Anytime the tool really gets loaded up, it threw a warning there because it plunged into the material pretty heavily. This is a full width cut. Let's speed it up a little bit so you can actually see why I don't like this tool path. You can see from the little blue path that showed us before that not only are we cutting too deep, it's not actually cutting out the whole shape. Yeah, this would be bad. If we ran that part, if we ran this code, the machine would be more than unhappy. We'd probably break a bit, if not break the machine. All right, so as far as I'm aware, you can't just switch this to different styles, so I'll just delete that and we'll quickly throw in another. Let's do pocket clearing. Adaptive clearing is fancy. In fact, let me go back one. I'll show you that. So this top one, adaptive clearing, is really good if you're going to be working with hard materials. It keeps the load on the cutter more constant, but it lengthens the path of the machine considerably. And since our machine is so speed limited, that really, really adds a lot of time to the cut. So, okay, let's go through this a bit faster now. Tool is good. Surface, let's select a silhouette. This one. Sounds great. The extents look reasonable. Passes. Tolerance is fine. Manual step over. Oh, step down. Yeah, we want that to be larger. 0.5. Stock to leave. 0.1. Oh, not 34 inches. That'd be bad. 0.1 inches. 0.1 inches. Okay. Lastly, helix feed in. Increase the angle so it doesn't take forever. Just click OK. What? Okay, so it wants a larger safe distance. Fine. Auto-generate the code. Now this looks a bit better. So you can see, especially if I hide, can I hide this temporarily? Yes. You see if you look from the side that it's doing 3 different layers, and each layer is going to be cut apart entirely. So let me go back here to the part and actually re-show the part that I'm wanting to create this from. Cutting files. So if we highlight this operation and again go to stock simulation, now you'll see the difference in pathing. Well, that was a bit too fast. Let's slow it down and show you again. So there's the helix entry. It's going back and forth and back and forth. And now you should start seeing that it's using 50% of the cutting width as much of the time as it can. Obviously, sometimes it's unavoidable. And this is what a roughing pass should really look like, that it's removing material with half the cutter-ish per operation. Let's speed it up a little bit. One more notch. It's still kind of slow. And then it goes way too fast. Yeah, welcome to the party. But you see it does that for the top layer, then it cuts out this pancake shape in the bottom layer, and middle layer, then the bottom layer, and you're good to go. So that is roughing, which is nice. And this is basically just to remove material so that whenever you put on the more fragile finishing bits, it's able to get down deeper. Well, not deeper. It's able to cut the final surface without loading up the cutter head as much. In fact, thinking that I'm probably going to use a 1/4 inch ball mill to finish this, or maybe a 1/2 inch ball mill, I think I will change the step down to 0.25. So that way it has more layers and can rough out some more of the material out here to the side. This will take longer, unquestionably. If this was going to be an MDF mold, then probably that feed rate and that amount of material removal was ambitious, we'll say, for this machine. But Now with only a 1/4 inch step down between each one, it's looking a lot better. Okay, the last thing we'll do now is actually use, let's do kind of like contour, but morph spiral also works. Let's try morph spiral. Let's make a new tool now, because a 1-inch flat mill is not going to leave us a very good surface finish. Let's create a new mill tool, and oftentimes for finishing we'll use a ball mill. In fact, this program must have heard me talking because it's already kind of loaded that up. 1/2 inch diameter, flute length of 1 inch should be suitable. Really, I'm just worried about the cutting elements because that's how the code generates everything it needs. All the feeds and speeds should be the same as before. Go ahead and select that. Silhouette, those two regions. Heights, we'll leave it alone. Step over. Okay, so now step over really matters. We have a 1/2 inch ball nose bit, which if we had a 50% tool engagement, that'd be a 1/4 inch, step over height. And this would leave a 7.3, or you could say 73 thousandths tall scallop cusp height. That picture shows you exactly what cusp height indicates. And it's basically the material left between ball nose passes. If you make the step over smaller, say 0.1, now instead of 70 thousandths, we're down to 10 thousandths. And that really makes everything much smoother. It requires less sanding from the engineer, or the individual finishing the mold, and less sanding means less opportunity for a person to introduce geometric error into the mold. So does it take longer? Yes, absolutely. A step over gets really small. Let's say we did something really crazy, 1/100th of an inch step over. Now you have a scallop height of, a 10,000th of an inch. That, for all intents and purposes, would be a perfectly smooth mold, but this path would be amazingly longer than if you just had the 1/10th of an inch step over. So let's go 1/10th of an inch for now with a 1/2 inch ball mill bit. By the way, there are advantages in having a larger radius and reducing cusp height, but obviously if you have a larger radius on the end of your ball mill bit, you won't be able to get as tightly down in these edges and corners, and you need to really watch what the maximum curvature, I should say the minimum curvature in your part is, to see if you can even cut that. You lead in an entry, okay, full retraction, yeah, all right. Let's say okay and let it generate its path and see if this is a path that we like. Still working, still generating. Okay, so obviously a lot of different paths here, but you can see it's going back and forth and back and forth and following that surface exactly. Now imagine if we hadn't done the roughing pass at all on this very deep cut mold. That little 1/2 inch wide ball mill would be trying to plow through however deep this is, 2 inches of MDF, 2 inches of foam, in addition to cutting at the surface. You don't want to do that all at once. So now what we can do is, instead of clicking an individual operation, we'll click the entire job and go to stock simulation. And we can visualize not only the tool that is in use, the cut that's being made, the passes that are being done. It'll show us the whole thing. And unfortunately, in this kind of awkwardly either too slow or too fast operation. But there comes the surface operation, which is going back and forth and back and forth and back and forth across the mold, finally getting that last perfect surface. That's the cut you really care about. That's the cut that's producing your mold surface. And I'll pause it for a moment to show you the benefits of doing this roughing pass. Notice that really that ball mill is only having to cut through, maybe I'd estimated, a 1/2 inch of material. As soon as the depth is getting too high, well, there the next pass of roughing was taken to alleviate load on the cutter head. So this kind of stepped pyramidal, inverted pyramid look really helps reduce load on the ball mill. Well, let's finish this, let it finish the simulation. These simulations are also really valuable for checking for conflicts. This is also the place that if you did define a model for the CNC machine cutting head, you could check for any sort of machine collisions. But this is the shape we should be left with. Notice it also color codes the surface by which operation it's cut by. In this case, there's a bit of Z fighting between the gray part and then the tan finishing pass. But overall, that is a really good surface finish. So accurate even that you can see, man, it's slowing my computer down to a pretty large extent. You can see the scallops it's going to leave. Those are fairly significant. And an estimate of machining time down here, 6 hours and 32 minutes. I hate to tell you, but usually those estimates are low. So this is a very big mold with a whole lot of material removal being cut by a machine that's not really that fast. So yes, this mold could take forever. It could take a very, very, very long time. Let's see how we can reduce that time requirement. If we edit this morph spiral, and instead of using a 1/2 inch ball, let's actually edit this tool and say, well, we've gone out and purchased a 2-inch diameter ball nose bit. We select that. Now if we go to paths, well, that 2-inch diameter at 1/10 of an inch creates 2/1000ths of an overlap. So let's, instead of 0.1 inch, let's go to 0.5 inches. And what scallop height does that leave? 64,000. Somehow that doesn't seem quite right. Let's not be so goey. So there we go, 22. Let's see what that does. So we've been able to triple the step over using a 2-inch ball nose. So if we simulate this whole job, I'll let it go as fast as it can this time. You see that now that change alone took our machine time from 6.5 hours estimated to 3.5 hours estimated. That's a kind of a strange looking 2-inch ball mill, but we do have some bits like that. So the surface in the main part of the mold is probably going to come out about the same quality as the other. But look at the compromise we made here in this sharp corner. The 2-inch ball mill could not, really machine that harsh curvature in the edge well at all. And you're left with, what could you even call it? Inaccuracy, shape inaccuracy. One way to make up for this is you could add one final operation. You could say, well, okay, I like the speed of the 2-inch ball mill. And you can come in and do, I think instead of 3D mill, it's called pencil. 2D. There's trace. Oh, come on, where'd it go? There's also rest machining, which is another option. Yeah, pencil, right there. So this is nice if you wanted to actually grab the corner of things. So let's actually make a new mill tool. Let's do a small 1/4 inch ball mill, something that's pretty tiny. Give it about a 1-inch cutter. Sure, just defining a tool pretty quickly. So this is a fairly small, fairly cheap ball cutter, 1/4 inch ball mill. So select that. How we're doing the pencil operation. Silhouettes. See if that's good. I'm not going to try to change too many things here. It should automatically detect the edges and go in and remove the remaining material. Yeah. So that's exactly what it did. Down here in the sharper corners, you see it's doing some, I would call that odd machine code remnants. That's garbage. But unfortunately, it won't do any harm. It'll just take the machine a bit longer. But over here, it's going to travel down that sharp curvature region. It's going to go up into the corner to take care of that. It's going to go right along this harsh edge left by that large 2-inch mill bit and do the same on the other side. So now if we look at the job and see what's left, by taking the time to do another tool change and another operation, you save hours of time on this surface finishing portion, and then lastly can sharpen up the edge cleanliness by using a 1/4 inch ball mill bit. And yeah, that still leaves a lot to be desired for me. It helps on the edge, but you see it's got that really odd and poor material that's left right there. So there's nothing saying you have to get into that corner perfectly. Keep in mind that rounding off corners is just fine. It just means the part you make from that mold will have rounded off corners. Really, in this balance, I would probably go back to something on the order of a 1-inch ball diameter bit. Select that there. Step over. Yeah, we'll call that about good. So this would be a nice compromise between cutting time and cutting accuracy, the amount of curvature we can adhere to. So obviously the path was longer. If we simulate the whole job, this would now be at probably 5-6 hours. So you have 4 hours, 17 minutes. So we added an hour of time over the 2-inch ball option. But lot of this surface cleanliness is a lot better. If you really wanted to eliminate all reasonable sanding tasks, if you wanted the machine to do all the cutting instead of people, you could take this down and get something in like the 5,000ths, 3,000ths range. And then the scallop height is so incredibly small, you don't have to bother with hand sanding anything. It's especially useful on aluminum molds because hand sanding aluminum, while possible, isn't fun. So let's do the whole job simulation. Do one last simulation here. Run it. So that smaller step over took the cut time back up to 6.5 hours, as you'd expect. But look how smooth the surface is coming out. The other downside of this is that, especially with some lower reliability machines, if power cycles during the 6 hours, or if machine breaks, or if it misses steps, if anything goes wrong in 6.5 hours, then it probably ruins the whole part. So you have to be a little bit careful signing yourself up for days long or 12-hour long cutting jobs. But there you go. This would be a CNC mold with very, very fine surface finish that you could just send to the CNC machine and say you're done after 6.5 hours. So now that you've made this auto-generated route, how do you actually put this into a file you can send to the CNC machine? And you do that by clicking Post-Process. There is a whole set of automatically installed post-processing files, and this is basically just what you might call the preferred recipe for individual types of machines. So filtering here, and is it not finding the list? Well, that's interesting. When we click vendors, it should have a large list of vendors. Okay, there we go. Thank goodness. So under setup, I clicked on use installed post-processing library. Now you can see all the different vendors of CNC machines who have preferred posts. The one that we use most commonly is called Mach 3, which I'm not seeing in the list. So apparently I've clicked something. So Haas would be like for the aluminum CNC machines we have in the lab. Linux CNC is it is an open source, nice CNC post. Tormach is another common kind of entry-level CNC, but Mach 3, which is normally here, it's not making an appearance. Personal post library has nothing. Installed post library. Now, Artsoft is the company that makes Mach 3, so maybe that's what they've changed the name to. Or maybe I was just looking at the wrong one. Hopefully it's here. Hopefully it's here. Come on. There we go. Thank goodness. Okay, so this is vendor, which makes sense. Artsoft, the vendor of Mach 3, makes sense. Here are the actual mills, so we can go down and they have both Mach 3, Mach 2. There's actually now also a Mach 4 software release set up. So our CNC machine is run by a piece of software called Mach 3. So you select the appropriate post, click the post button, say where you want to save it, and it will go through translating all of that path information into text. These are XYZ coordinates. Lots of setup information here at first, and these are what are called Gcode files because everything's G90, G94, G91.1, G40. All of those commands mean something to the CNC machines. If you want to know what that code means, there's an excellent Wikipedia summary of all of those Gcodes. Different types of software understand different portions of the entire standardized Gcode. Everything up here in the front is really just a comment. Everything in parentheses is just help for the user of the machine. So it's just reminding you what tool 1, tool 2, and tool 3 should be before you start this part. Now, with our machines, you are the tool changer. You have to undo the tool. You have to mount the tool. There's no ATC involved. But with some fancier machines and more modern hardware, they'll automatically switch between those tools based on the index T1, T2, T3. You might have a 40 position tool changer, and you just go by what's already mounted up in there. So it's very interesting if you want to dive into what all these codes actually mean, but there's our pocket operation. You can go on down and find the different roughing stages we've done, the different clearance stages, but this is a huge amount of code. I mean, where's the line count? Oh, it's over here. So 41,533 lines of code, which is pretty big, but we've sometimes cut parts with 700,000. I don't know if we've gone over 1 million very often, but it's pretty common to have massive, massive numbers of Gcode commands. So you should have that file automatically generated. In fact, there it is, the .tap file. If we open that up with a text file, or text editor, we can see that inside that tap file is just a bunch of text, and it's the Gcode. Be careful opening this in Notepad, because honestly it's sometimes so much text that Notepad kind of has a hiccup or 5. So anyway, that's how you go through the process from nothing to Gcode, and it's all about the same for doing a non-planar parting line mold, with the exception that now you have to do the entire surface with a ball nose bit. You don't have the luxury of having a flat parting line out here. You don't have that flat planar region. It's going to be curvy. So you don't get to accelerate and reduce cutting time, and by using a large flat 1-inch diameter cutting bit, you're stuck with using ball nose bits all the way around, and it just takes longer. So like I said, for many, many different reasons, it's harder to make the mold file, it's harder to cut, it takes longer to cut. Only use non-planar parting lines if you have to. So that's how you translate things into Gcode, and that's usually the last step as you move your part design out of the digital 3D world and into physical reality.